see in more detail or something like this. So I'll take it really fast.
Yeah, I was trying to understand the difference you're talking about between the is even example in lean versus FOL.
Mm-hmm.
Can you say again, like, what piece in the FOL is like kind of missing? Is it like the translation between the two?
Yeah, so I think so I have a list of things actually that let me just. So I think the really big difference is that you're not switching context when you're doing computation. Maybe you're doing it implicitly, but your type theoretical reducer is already doing this computation aspect and you're piggybacking that. And that's very important also to ensure that basically the kind of reflection you can do is completely sound. You have to have proof. I mean, in order to use this, you have to have proved or admitted this equivalence proof, and then everything becomes easy. But in fall, you didn't have to have your summary proof. You could even just say anything that I assume is true, and you could just go with that if you wanted as a reflection principle. So I think that's a big difference. I have a few other differences that I think are important. So the reason why, like, the shift is really because now we have computation that's in the first class as opposed to explicit non-conditional computation, and that's like really because it's true that in many cases, in many proofs, you just are doing computation anyway, so you want to have a solid condition for this. And the type system itself enforces the soundness of reflection. Like you kind of have to have a theorem that you reflect, and the theorem is proved sound, and the typing of your proposition, like your equivalent statement as a proposition is enforced, right? And things like that. But at the same time, there is a need to do this kind of reflection because what you do by deduction feels different than what you do computationally, but they're integrated in the system. So the type theory is unified, while in FOL it was also a way of like thinking about theories that you might want to have. So everything was more explicit in that respect, that the theories you have you built, like nothing was really built in, everything was kind of defined explicitly. And then I guess I would say the native decidability, the fact that you have this part and this part, which looks more simple. I should keep the version that is not as simple, but it's also pretty simple. This is mostly sugar, right? But you have, it's recognized that it's such a common thing to do that you have facilities for it. So I think, I think also like in this case, because we're dealing with decidability, we can also reason about negation as well, using the decidable statement. That would be something that you would have to do separately in FOL. So there are these few differences. And also the computation that happens is proof producing in mean. So you're building up your like you end up getting a proof term anyways for all of that, and you can do it even through the computation. Yeah.
Can I ask you, so as long as they really use the plus kernel option, which is fine, because it's just skipping elaboration and still giving a proof term. But there's also this idea of adding the code compiler to the trusted base when you're working with this. Is there any like research on in between of like adding a little bit of trust to what's happening unfolding with tactics like this for the side, or just what do you think about that?
Yeah, so I think the only reason that I was using I think it was just so I guess it was only like to kind of show that this can be sped up to bigger numbers. I'm not sure if there's any soundness implication? Do you think there is a soundness implication?
Not for plus kernel, because it just passes the elaboration to the kernel. There's another version that adds the lean compiler to the trusting base, and there can be soundness issues with that.
Okay, I see. Yeah. So I think that's a good question in general, especially in the context of reflection. So reflection traditionally kind of makes all bets off, right? And kind of how do you make sure that your reflection is reasonable? There's a spectrum of things you can do, and I think in that case. So in this example, I feel like there's not too much increase in for this Boolean reflection. There's not a need to increase the surface of trust because, like, as long as this proof makes sense and you have you can check it with your kernel anyways, then you don't need to increase the surface of trust. So I think I would be curious to see in which cases do you actually want to increase the surface of trust, and maybe that involves, like, if you're not doing proof producing computation, then that's kind of where you might have to increase the surface to a certain point. So for example, if you're connecting Lean to an SMT solver, then you want to trust, most systems just would trust the SMT solver, and that's a pretty big trust. But you could have a system that more laboriously produces proofs of what's happening there, and then you wouldn't need to trust. I don't know that. That's
That's a lot.
yeah, okay. Yes?
While this is interesting, and thank you for showing it, I think if I understand correctly, the reason why people don't usually just leave deciding a particular judgment to a decision procedure is that sometimes, at least in this case, the decision procedure is easily proof terminating, but in most, I'd say more interesting cases, just like I have a decision procedure, I prove that it terminates on like pen and paper, but I don't have a lead proof that it terminates. And then that can become tricky, right? Because to use something as a recursive definition.
Yeah, but I think that's a decidability issue, which is maybe even on orthogonal to the rest. Like, if your thing doesn't terminate, then the answer is unknown, and you have to maybe fall back to some other mechanism. But it seems like as long as you're not like using it as a type, but as a computation, the fact that it doesn't terminate means you can still use it positively as a computation when it terminates.
Does that apply to Rocketeer Improver too? Because I don't know, it's been a while, but I remember like having challenges around like non-terminating functions in Rock. And also,
yeah. So this is because there are challenges around non-terminating functions. Also in Zapping, for example, you have to prove your functions terminating because by the Curie-Howardized program, if you have a non-terminating function that you use as a type, then you can have anything from A to B. Right?
Yeah. I'm curious too, like, okay, so like this is like these techniques can prove things about the behavior of like terminating like functional programs. I'm curious if these techniques or similar ones might be able to like prove things about the behavior of non-terminating programs that just have side effects, like that continuously run and like.
Okay. Yeah, I think it could be interesting. I mean, there's a lot of work about reasoning about non-terminating programs. And I guess the question is, what would you do differently for non-terminating programs? Like in the context of like analyzing your programs, you might just do a different analysis, but the basic way of analyzing could be fairly similar. I don't know. I think it depends. It's like I guess the main machinery is how do you do things soundly, and I think that machinery kind of works regardless of the design or like how the programs are in terms of Okay, thank you.